Welcome to next class 9th. Okay, so in the previous class we have learned regarding beta alumina and we have completed whatever necessary points should be learned in beta alumina. So today we'll go for silver iodide. Okay, Ag plus ionic conduction. This Ag silver iodide at low temperature. Okay, at low temperature this silver iodide, okay, AgI, so they adopts woodside structure, woodside, WURTZIT, woodside structure, okay, or sometimes we can say zinc blend structure, okay. So here the Ag plus whatever ions is there, they fills the obtained holes, okay. They will going to move, okay, and they are going to fill half of the obtained holes in a closed packed array of iodide, okay, I minus, at about 146 degrees centigrade. You can see that it transforms to the BCC, that is body centered cubic structure with Ag plus. This happens at 146 degree and BCC structure, and you can see the Ag plus filling a small fraction of available tetrahedral sites, okay. So Ag plus ions are about they start to move in the tetrahedral sites, okay. So this is how and the cation sublattice. So this is how the, I can say, the conduction in the silver iodide, it takes place under the phase transition at the value of phase transition. I can say this is very much important. Undergoes phase transition at around 146 degrees centigrade, okay, and at high temperature they are going to form the alpha AgI. Which is having a high conductivity, okay. This is alpha AgI is having the high conductivity value of around near to 1 Siemens per centimeter, okay. So Siemens per centimeter, and they have 4 order magnitude larger, 4 order magnitude, okay, magnitude larger, I can say, the larger conductivity than the beta silver iodide, okay. Sorry, not beta silver iodide, this is alpha silver iodide. So having around 1 Siemens per centimeter conductivity, okay, and that is 4 order magnitude larger than the beta AgI, so at room temperature. So this is what we have seen, that it is having the true phase transition, that is alpha AgI and the beta AgI, okay, and this is having the least conductivity value, and alpha AgI is having the 4 order larger magnitude of conduction near to 1 Siemens than this beta form, okay. So this is why, and even the activation energy, if you see the ACTN, activation energy, okay, and this for the conduction of alpha AgI is very less, that is almost 0.05 electron volt, okay, very less, zero point 0 electron volt, and the structure suited for here for the easy motion of Ag plus. So that's where the structure is made here, and that's what woodside I said here, okay, woodside structure. And the ionic conductivity usually they decreases here. The ionic conductivity decreases in this on melting at 555 degrees centigrade, okay. If you melt at 555 degrees centigrade, the ionic conductivity usually it's going to decrease, okay, for alpha AgI. Beta AgI, it has woodside with structure of woodside, okay. So beta AgI has a woodside structure, and with iodide in the HCP, okay, hexagonal close packed structure, I minus ions. This will be made like this, okay, I minus in the hexagonal close packed structure in the woodside structure of the AgI. So here you can see that Ag plus ions, they have transformation or the mobility towards the tetrahedral sites, okay. And in alpha AgI is BCC, okay. Here the structure will be body centered cubic here, and I minus lie at the corners here. I minus they lie at the corners of the cubic structure, and the body centered position and the body centered position, okay. So this is how the I minus lie, and Ag plus ions are readily move from one side to a next like a liquid like manner, okay. So Ag plus ions move from one side to another side of this like liquid manner, and you know the fascinating of this Ag plus here, is polarizing cation. Ag plus is a very good polarizing cation. Okay, so this is very good polarizing cation, and it's usually outer 4d electrons. Okay, in this Ag plus, see the outer 4d electrons are ineffective. Okay, are ineffective. Outer 4d electrons are ineffective, and ineffective in shielding the nuclear charge. That is ineffective in shielding the nuclear charge. Ineffective in shielding the nuclear charge. Okay, so this is what about the Ag plus ions. And I minus is a large polarizable anion. So if you take this I minus, it's a large anion with polarizable capacity. Okay, easily polarizable. So anion, and between this you can see a covalent bond is formed. Okay, this is very much important. Between this AgI, there is a covalent bond will be there. Okay, so this is what about the AgI. And if you partial replace this Ag here, partial replace of Ag with rubidium Rb. Okay, so rubidium, like in case of you get an RbAg4I5, this composition RbAg4I5 like this. Okay, so such composition, they have high ionic conductivity at room temperature. Okay, they have high ionic conductivity. Just replacement of Ag by Rb, you can have the high ionic conductivity to the level to the range of around 0.25 at room temperature, 0.25 Siemens per centimeter at room temperature. Okay, so this also you have to keep in the mind. And activation energy is 0.07 electron, very less. Activation energy, ACT, activation energy is 0.07 electron volts. Okay, so this amount of and the amount of electronic conductivity, if you see in this electronic conductivity, this is ionic conductivity. Now electronic conductivity, if you see, is negligible in this case. Okay, in rubidium case. Okay, it's a very negligible, and you can see about 10 to the power of minus 9 to the level of 10 minus 9 Siemens per centimeter at 25 degree centigrade. Okay, so this is what about you have to see the what you say the conduction in AgI here. Now if you see the phase diagram, I will write here. So I will go for the T diagrams here. Presentation. If you see, this is how I can go for like this. All four corners you can see here like this. Okay, here one like this body center. So this is the crystal structure of alpha AgI. So this structure is crystal structure for alpha AgI. Okay, alpha AgI showing BCC arrangement, showing this is a BCC arrangement. BCC arrangement showing BCC arrangement of I minus. Okay, BCC arrangement for all body centered 1 2 3 4 5 6 7 8 and centroid. Okay, this is how the crystal structure for alpha AgI showing the BCC arrangement for of I minus anion. Okay, so this is what. And if you see the structural movement here, so sometimes we will go for like this. Now if you see the structural movement, otherwise this is very complicated. Simple, I will go for out of this one box I will take it here like this. Okay, so 1 2 3 4 iodide is there here, and if you see that there is something like that, this is how the movement will be there here. Or you can show this is the middle one here. Okay, so sometimes you can 2. Okay, this I will take it as a something here A. Okay, this I can take it as a B dash or B like this in between. Okay, so here like this, then here like this. Okay, or C like this. So here also there is a, so these are the what you say the sites available for the Ag plus ions. Okay, so here we can see these are the sites, tetrahedral sites available, for Ag plus ions. Okay, so these are the sites available for Ag plus ions, 2 mobile, so tetrahedral sites or sometimes octahedral. So like this small slides you can see here one side, here one side, here one side, here one side like this. Okay, so these are some of the sites so for Ag plus ion to move here. Okay, in this, so this is how the cubic structure here. And if you see the, you can show for the phase diagram also. So I will go for the phase diagram here. So like this you can show phase diagram also. for the mixture here. So we will take it as a 0 here. 100 to 600, 100, 200, 300, 400, 500, 600. Okay, from 600 to 230 something here, like this you can do it here. 230 or something here, like this you can make a phase here, like this. AgI plus liquid and something here under 0 you can make like this. Okay, here something like that, and here also, here you can make two cases like this. Okay, so here RB Ag4 I5 plus AgI, and here you can see RB2 I Ag RB2 AgI3 plus RBI. Okay, so here you can take it as RB2 AgI3 plus AgI. Here you can take RB2 AgI3 plus liquid. Okay, so this is your RB Ag4 I5 plus liquid. So here up is liquid. Okay, so here your it is AgI plus liquid. Okay, similarly here RBI plus liquid, and here down temperature RB to AgI3 plus AgI. Okay, and here there is a concentration of RBI, and here AgI. This is your 50% AgI. Okay, so like this, then here 10, 20, 30, 40, 50, 60, 70, something like that. Okay, and you can see, so this point is nothing but RB2 AgI3, and this point. Okay, so this point something here is nothing but RBAg4 I5, like this. Okay, so this is a phase diagram here, so you can show here phase diagram. See this phase diagram of AgI and RBI, rubidium. Okay, so just if you add this rubidium into silver, so you can see that it is going to give a very good conduction here. Okay, so these are the three modes of the conduction here for AgI. The first one is the crystal side for the AgI, body centered centered cubic. The second one is small sides of the, how the sides will be there for the movement of the Ag plus ion into this, and by which we can see the conduction takes place. And this is the phase diagram here for AgI and RBI combination, where we can get this composition which is having the highest conduction value at a room temperature compared to the alpha AgI. Okay, so this is what. Now if you consider this phase diagram here, so two binary compounds exist here, that is two binary compounds, that is your RB2 AgI3. So RB2 AgI3, this is one binary compound, and here RB Ag4I5. Okay, RB Ag4I5 here. So these two binary composition compounds is exist here, and the letter here. So if you see here RB Ag4 or here RB2 AgI3. Okay, RB2 AgI3. So they are going to melt here to AgI and liquid. Okay, so AgI and liquid here. So let me see. So AgI and liquid here. Okay, it's almost here. Okay, so this is what happening here. Yes, AgI plus liquid at 230 degrees centigrade. So if you see here 230 degrees centigrade. Okay, so at 230 degrees centigrade they are going to melt here. So AgI plus liquid, like this. Okay, AgI plus liquid. So in this way at 230 degrees centigrade, and it has a low limit of stability, and it decomposes to AgI. So it decomposes to AgI, and you can see here RB2 AgI3, AgI and RB2 AgI3. So they are going to decompose. Okay, so RB2 AgI3 and AgI. So this is happening. So they are going to decompose here in this case. Okay, so here and RBAg4I5 here. Okay, so they may be cooled below here. If you see below 10 degrees, so slowly you have to do, otherwise it also will undergo the what you say, the decomposition. Very slowly you can cool under the cool temperature here without decomposition. Okay, so this is what. And so you can see minimum the range of the uh, you can say the anions may be substituted. So if you take anions, okay, so they can be easily substituted. So you can substitute this partially for iodide I minus. Okay, and you can see you are having the high conductivity. So you are going to have high conductivity. You are going to have high conductivity. For example, if you see Ag, you can see 3Si. Okay, so for I and sulfur is substituted for some of the anions. Okay, so they are having high conductivity. Similarly, you can take some examples of what we can give. Yeah, Ag7. So this you can give Ag7I4PO4. So here phosphate. Okay, anion. So I is little of the I minus is substituted by phosphate minus 3, like this. Okay, so this also you can show, or you can show Ag6I4 tungstate WO4. See here, tungstate AgI4. Some of the iodide is substituted by another ion, that is your tungstate. So like this. So what is the main problem, or what is the main advantage of this is, if you substitute some of the ion with more anion here, another this one, so that will increase the again conductivity. Okay, so that will increase again, give good conductivity, and also thermal stability. So this is important, and also give thermal stability. So this is here. So double advantage is there if you substitute some of the partially I minus to some other anions. Okay, so that will have very good thermal, and they can be used for the most of the electrochemical cells, and such things can be used for most of the electrochemical cells. Okay, so this is also you can keep in the mind. Okay, and it is also possible to replace both now. So you can replace both Ag plus and I minus simultaneously. Okay, so you replace this Ag plus and I minus simultaneously. For example, if you replace Ag plus with Hg plus 2, like this. Okay, Ag plus can be replaced by Hg plus 2, and I minus by your selenium minus 2, like this. Okay, I minus by selenium minus 2 you replace, and Ag plus by Hg plus 2 you can replace it. Okay, so this also you can do it in for example, if you take the example of the same in I will write here Ag 1.8, Hg 0.45, Se 0.7, I 1.5. See here, so in this compound. Okay, so I have substituted Ag plus with Hg plus 2 here, Hg 0.545, Ag 1.8, and selenium, so I minus with selenium minus 2, selenium 0.7, and I is 1.5, like this. Okay, so this is the best example for partial replacement of Ag plus 2, Hg plus 2, and I minus 2, selenium minus 2, like this. Okay, this becomes a very good composition for the high conduction and thermal stability. Okay, so this also we can do, or sometimes you can replace Ag plus 2 rubidium, just now we learnt here Rb plus and I minus to Cn minus. This also I minus to Cn minus. In one example you can give Rb Ag4 I4 Cnc. This is what. Okay, so this is example. So some of the Ag you have replaced with Rb and I minus with Cn. So this also becomes a very good composition here, for which you can see that it can have the very good value for the conduction. Okay, so this also you can do replacement. Okay, similarly if you see the AgCl and AgBr, okay, so they are, because AgI we have learned, and if you see these two, so they are having less conduction. So why they are having less conduction here? Because they are having less covalent bond here. So this is having high covalent bond, high covalency, but if you see in these two compounds, they are less covalent, in nature here. Okay, and that's why you can see they have different crystal structure also. So these two have rock salt structure, AgCl and AgBr. They have rock salt structure like an NaCl, and you can see that alpha AgI. So this is having the very complex structure. Okay, so this is what the difference you can see between AgCl, AgB, and this one. Okay, and you can see the usually the crystal structure whatever is there in this rubidium RbAg4I5. So they are having different from alpha AgI. They are having different from the alpha AgI, this one too. Okay, and they contain Ag plus ion. Main thing is here Ag plus ion, mobile network, and they are going to they are going to move in the different network of the in the tetrahedral sites, okay, and the conductivity tetrahedral sites here. So this is what we can see, the conduction in the AgI. Okay, so phase diagram you have to show, and you have to show the conduction here in the structure figure A and B, and explain this much. That is, I think, more than sufficient. And you can see even anion conductors and applications are very much required, is very much important in some of the solid electrolytes here. If you see the anionic conductors like PbF2, okay, so where you can see fluoride structure, we can see that this is a fluoride structure PbF2, and they are having the fluoride structure and has F minus here. Okay, they are going to conduct at high temperature. At high temperature they are going to show conductivity at 500 degrees centigrade around, okay, 500 degrees centigrade to 5 Siemens per centimeter. See here, very high, 5 Siemens per centimeter anionic conductor. Okay, and the sigma value increases slowly till you can see 222 degrees centigrade, and under its melt the sigma goes on increasing. So this is what about the anionic conductor, that is PbF2. Even oxide ion conductor also we can see, oxide ion conductors, solid conductors, solid electrolytes. Okay, so oxide ions, so where they are using in oxygen sensor, used as oxygen sensors they are used. Okay, and even for the pumps, pump they are using pumps. And you can see solid electrolyte, solid oxide fuel cells, solid oxide fuel cells. In that also it is short formally SOFCS, solid oxide fuel cells they are using here. Okay, and sometimes you can say YSZ, that is atria stabilized, atria YSZ, zirconia. Okay, so this also you can see the atria stabilized zirconia, which is a very good conductor, I can say. Okay, and here I2 minus O2 minus, that is oxide ion conductors at high temperatures. Okay, they are having around 10 to the power of minus 1 to 10 minus 2 Siemens per centimeter conduction at high temperature at 800 degrees centigrade around. Okay, and if you see activation energy, so it is around 0.8 to 1.3 electron volt, 0.8 to 1.3 electron volt will be activation energy but at low temperature the conduction is small. At low temperature the conduction is small. Okay, so this is what you can see, some of the anionic conductor and its application. So one more application important is your solar cells, that is they will ask is sodium sulfur cells. Okay, so we can draw this diagram of sodium sulfur cell, which is having something like this can. Okay, and you can have this U shape like this. Okay, so solid electrolyte is placed here. So this is your solid solar cell. They will ask sometimes 3 marks 4 marks question with the application of solid electrolyte. Okay, in this one. Okay, so you can show here like this and you can see this is the electrolyte here line. Okay, so this sodium sulfide discharged, and this is your aluminum oxide insulators, aluminum oxide which act as insulators. Okay, and this is your sodium solid electrolyte beta alumina solid electrolyte is placed here. This is your minus charge and this is your plus charge. This is minus charge and this is your plus charge. Okay, sodium aluminum oxide, so aluminum oxide insulator is, and this is here it is sodium is taken. Okay, so this is how the sodium sulfur cell is, we can mention here the best application of beta alumina, how it is been used in this cell. And the cell reaction you can say 2Na plus 5s is a reversible to give Na2s5. Okay, so you are going to get around 2.03 volt from these cells. Okay, so this is a reaction you can show, that is 2Na plus 5s giving Na2s5 with the output of 2.03 volt here. Okay, so here the sodium sulfur cell, they utilize the Na plus here. Okay, from this beta alumina they utilize the Na plus from beta alumina solid electrolyte, and it is having high density, that is secondary battery. It is used as a high density secondary battery, this one. Okay, and the ratio of if you see power to mass and high energy, I can say high energy power to mass ratio. It has high energy power to mass ratio. Okay, so they are having high energy power to mass ratio, high energy power to mass ratio, this battery. Okay, so that is one advantage here. For electric vehicles and power stations, they are used for electric vehicles. Nowadays they are using electric vehicles or power station. In most of these power stations, electric vehicles, okay, load leveling machines, okay, they consist, they are being used, this cells is being used. Okay, and it consists of molten sodium as an anode here. So here we have written as a sodium here, so molten sodium, so they have been used as an anode here, minus. Okay, so here, and you can see, and the molten sulfur as a cathode here. So this is what here, so molten sulfur is used and it is acting as a cathode here. Okay, so this is how positive negative charge will be created here. And these two, that is your anode and cathode, is separated by the molten sulfur here, molten sulfur, okay, cathode, and they are separated by the beta alumina solid electrolyte here, this one. Okay, they are separated like this, beta alumina solid electrolyte, this one. Okay, and this beta alumina fabricated in a tube way, so that is tube, closed tube. Okay, at one end like this, with the sodium inside and sulfur outside. This sulfur is outside and the sodium is inside like this. So this sodium is inside and sulfur is outside. So this act as a, so beta alumina act as a separator here. So between this sulfur and the sodium, that is your positive and negative charges here. So this is what. Okay, and you can see here the molten sulfur, it is a covalently bonded solid here. Sulfur, you can see here, so molten sulfur whatever we are using, so it's a covalently bonded solid here, and it is acting as electrical insulators. Okay, so bonded to this solid here like this. Okay, and they are acting as insulators here. So I can see here aluminum oxides, so they are acting as insulators here, electrical insulators. Okay, and the cathode material used therefore consist have the graphite felt. Sometimes they are using graphite felt here. Okay, and you know the cell mode of and the outer cell here, so they are made up of stainless steel here. Okay, so outer mode of this one, so they are made up of stainless steel. Okay, and they are also acting as a current collector, they are also acting as a current collector. So outer vessels here, and they have the less discharge reaction. So discharge reaction, you can already have going you total net reaction here. Since the net the discharge reaction, you can show in this way, xs giving you Na to Sx. Okay, so 2Na plus X of sulfur here, so give you Na to Sx like this. Okay, so this is one typical discharge reaction, you can show it, and it depends on the level of charge, okay, in the cells like that. And this sodium sulfur here, Na and S cells, okay, so they operate at a range of 300 to 500 degrees centigrade. Okay, so lowest temperature at which discharge product is molten in state. So this is what I think application you can show for sodium sulfur, and this is a reaction you can show. Okay, and this reaction and how its applications, anode cathode, what they are used, how it is separated by beta alumina. And here also you can see the conduction is only because of the Na plus ions movement, and it is a very good secondary battery with high energy power to mass ratio and giving you 2.03 volt. Okay, so that's why it is used in most of the electrical vehicles and other application parts. So I think this is more than sufficient, and we have learned here the anionic conduction here. So they are also very good used, and have the most applications in sensors and in most of the fuel cells. Okay, one example you have taken, and we have learned regarding regarding Ag plus ions. Okay, conduction in AgI. With phase diagram we have learned BCC and how this Ag plus ion move, and even we have seen the composition phase diagram of the silver iodide with doped with rubidium iodide, and this is how the conduction increases. These all things we have learned in this today's video, and I think we have completed both now whatever requirement for beta aluminum solid electrolyte and your Ag plus solid electrolyte. Okay, so I think we completed here the two concepts of the solid electrolyte conductivity. In the next video we'll go for some other concepts of the unit 4. Thank you.